Lisa.
All right, hi everyone. I'm excited to be here to talk to you today about some work we're doing with blends of OPC and CSA in my lab. A lot of this work was done by my undergraduate research assistant who worked through the COVID period, has now graduated, Anthony Wong. So we'll talk a little bit about the goals of this project, why we're undertaking this, and then look at performance of the systems in terms of hydration kinetics and setting time, discuss what we've learned about dosing retarders in these blended systems, and then how the blends generate strength and their relative levels of durability as well. My hope through this presentation is to continue building a bridge between where we are today with our current understanding of ACMs and in particular calcium sulfoaluminate cements and a place where we can have an optimized and normalized usage of these materials. I see these materials as a tool in the toolbox for increasing the sustainability of our concretes. I've shown here some data adapted from Gartner 2004, where he showed that you can obtain as much as a 45% reduction in associated embodied CO2 with calcium sulfoaluminate and beolytic calcium sulfoaluminate materials when used in a 1-to-1 ratio. But in addition to that sustainability, calcium sulfoaluminate cements have a lot of benefits. Most predominantly, they're extremely fast setting. As Cameron mentioned earlier, you can obtain set in as early as 5 to 10 minutes without retarder. And along with that fast setting time comes also high early strength gain rates. So we can use these materials to accelerate construction schedules and perform rapid repairs. There are a lot of challenges associated with this material because it's not been used as prevalently as OPC, so we don't have that giant knowledge bank in most of them. And some of the challenges are associated with that fast setting benefit that we've just talked about, because it can become an impediment to construction. If you have to get your concrete from a batch plant to a site, you're going to need more than 5 to 10 minutes to do that. And similarly, if you're placing a large amount of concrete on site, you'll need a way to delay that setting time. So we need to build out our resources for controlling these reactions and giving us enough working time to place the material. CSA cements also, because of their high alumina content, do have a higher cost than OPC. And so that can kind of prevent some users from wanting to use this sustainable material. And then finally, there's a large amount of unknowns regarding durability with CSA cements. So our hypothesis was that perhaps we could address some of these concerns through the use of a CSA OPC blend. So our idea is to maintain that fast setting time and early strength development, but use the OPC to dilute the system and enable us to extend our working time. Similarly, perhaps we could going the opposite direction, use CSAs in small proportions to provide alternatives to chloride-based accelerating admixtures. So we could get an early set time and early strength gain without adding chlorides to our system. We also, when doing that, can maintain some of the sustainability gains associated with CSA, albeit in a lesser amount than if we use a 100% CSA mixture. It'll be more akin to the sustainability gains that we get from use of SCMs, which are used to substitute out a proportion of the OPC rather than the full OPC content. And then finally, by diluting or by lessening the proportion of CSA in the mix, we're going to reduce the total cost of using that material while hopefully maintaining some of the benefits. There is some challenge with using CSA OPC blends though as well. We really have very little published data on this material, although I'm hearing that it's used fairly frequently on an industrial scale. And so some of the knowledge needed to choose the correct proportions and to understand what the effect on setting time and strength development and durability is quite limited. So we hope to fill in a little bit of that information in this presentation. So Cameron was talking a little bit about different types of CSA. I've shown the 4 proposed types of CSA on the screen here. The one that we used in this study is most akin to a type A accelerating additive. So this is a type of cement with the highest proportion of yeelimite, just shown in the first column here, which is the fastest reacting and most reactive component within the CSA cement system. The cement that we used, I incorrectly titled my talk, and it's not actually a CSA, it's just this type A cement. I do also want to highlight how we've named things moving forward in this presentation. Whenever I have a 100% OPC or 100% CSA system, I tried to call them OPC or CSA, but all other blended mixtures are shown as a proportion of OPC to CSA. So this 90-10 mixture is 90% Portland cement, 10% CSA. We cast our mixtures with you can see the mixed design quantities on the right side here, a pretty low water to cement ratio. Previous BCSA diffusivity literature had indicated that you get much better performance with CSAs at slightly lower water to cement ratios than what you could use with a Portland cement. So we wanted to start out on a good foot as far as durability, with a little bit lower water to cement ratio. As you can see from the chart here, we were able to obtain pretty good workability through use of a superplasticizing admixture, and we did successfully air and train all of our concretes. So first, let's look at the effect of these blends on setting time of our mixtures. We'll focus first on the isothermal calorimetry plot at the bottom of the screen. And what we can see is our OPC shown in black, and it has a pretty low heat release compared to all of the blended cements and a significantly longer setting time. So the time to reach our maximum rate of heat release with the OPC was a little over 6 hours. Whereas as soon as we started substituting out OPC for CSA, we significantly shortened that time. So we went from about a 6-hour max rate of heat release to about a 4-hour max rate of heat release with only 10% CSA added to the mixture. We continue to see additional acceleration through use of higher CSA components. And this translated as well to our VICAT setting time, shown in the top of the screen. So by using a 5% substitution of CSA, we reduced our initial set time by 33% from 203 minutes to 136 minutes. And we reduced setting time by 87% by increasing that CSA percent from 5 to 10%. So a couple things that we noticed from this data is that if you are trying to use CSA simply for the accelerating portion, you probably don't want to use greater than 10% CSA in your mix. We didn't really see much in the way of acceleration at greater levels than 10%, primarily because the set times became so incredibly small. Everything 15% CSA and above was 16 minutes or less to initial set time. And so actually what I would recommend is at 15% CSA or above, you actually employ use of a citric acid retarding material to delay that set time a little bit, whereas we can obtain those accelerated and yet maybe not too accelerated results with CSA at lower proportions. Speaking of setting time and retarder dosage, we had struggled a little bit in figuring out how to actually calculate the dosage needed to obtain good setting times for these mixes. We started out, well, let me back up a little bit. You can find in literature the effect of citric acid on OPC cement, and it is a very, very effective retarder. A 0.5% by mass dosage of citric acid in 100% OPC mix results in 160 hours of set time delay. So we were a little bit nervous that if we used more typical retarder dosages in a CSA OPC blend, we would end up with an almost never setting mixture. And so we started out dosing our retarder based on CSA weight, but and that seemed to work fine for our 100% CSA mix and for our 50-50 CSA OPC mix. But when we went to smaller percentages of CSA and larger percentages of OPC, the relationship between retarder dosage and initial set time changes radically. So we went back and tried to rethink this a little bit. And I've shown here retarder dosage based on total cementitious content relative to the initial set time. And you can see that things align a lot better when we normalize by total retarder dosage. And the results are even more aligned when you normalize by just OPC mass at all. So we have more predictable results when we proportion retarder based on the OPC percentage rather than based on CSA mass or total cementitious content. Right. So at the beginning, I postulated that perhaps we could use CSA as an accelerating admixture, and this slide shows the results of that. And what you can see is we were not able to obtain the 4,000 PSI rapid repair conditions that we had hoped for in this mix, but we can see that with increasing amount of CSA, so we go from 0 CSA at the top to 100% CSA at the bottom, and it's quite linearly related how much CSA you have versus the rate of strength gain initially. So we see a pretty linear relationship, except for this one hiccup, between CSA percentage and initial strength at the 4-hour time period. This increased rate of strength gain does not continue to 1 day though. By 1 day, we see that the OPC and the CSA OPC blends have pretty similar strength gain. Although the 100% CSA mix has exceeded the strength of all of those mixes significantly at 1 day, reaching about 6,000 PSI compared to 4,000 of the other mixes. However, over the long term, we see sort of a flip-flop in that relationship. Our CSA stops gaining strength at about 28 days and starts to actually lose a little bit of strength or stay pretty consistent. Our OPC continues to gain strength, and our OPC-CSA blends gain quite a bit more strength over that time period. In the end, the blends ended up with strengths between 8,000 and 10,000 PSI, whereas the CSA and the OPC mix were between 6,000 and 8,000 PSI. So there could be some compressive strength gains to be obtained from using these blended materials. And we saw similar performance at 28 days on relative strength of all of these mixtures. And so finally, we did an assessment on durability, focusing in on chloride diffusivity. And so we looked at only a couple mixes. This work is quite a bit more involved. And so we assessed OPC, 100% OPC mix, the 100% CSA mix, and a mix that's 50-50 of each of those materials. And overall, what we can see is that the OPC and the blended mix performed very similarly, and the CSA had slightly better performance at 28 days. And the diffusion coefficients as well are shown below. We see pretty similar performance from the OPC and the blended mix, and slightly better performance from the 100% CSA mixture. I've also provided you here a little bit of an overview of most of the diffusivity data that I can find published at this time compared with our results. And there's a couple things that we can get from this chart. First, we see that the CSAs and OPC blends have relatively similar performance. At 28 days, the Raven study showed a slightly reduced diffusion coefficient for CSA mix, but they actually tracked changes over time, and by 56th day, the CSA was performing much better than the OPC. And we saw similar results in our study with slightly improved diffusivity in the CSA mixture compared to our OPC, and then that OPC-CSA blend has, again, a similar performance, although in our study a little bit greater diffusivity than the CSA alone mix. And I should note as well that all of the other studies shown here are the Class B CSA, the beolytic CSA cement, whereas ours is that Class A. So they're a little bit different materials, hence the different behavior. Great, so the main takeaways from our study, we definitely can use CSA as an accelerating mineral admixture. It will accelerate both our setting times and our initial strength gain rates. Higher use of higher proportions of CSA will increase the rate of acceleration. But if we are not careful, we may then need to go back and add in an additional retarder to control that setting time. Dosing of the retarders is most consistently done based on the amount of OPC present in the mixture rather than total cementitious content or CSA content. And finally, we found that CSA OPC blends obtain satisfactory strength and durability relative to OPC, and maybe in some cases improved performance. So I've shown everyone I cited there, and I'm happy to take some questions if there are any.